Hi, good morning everyone. Welcome to day 2 of Embedded World, and thank you for attending this session with us. This morning I'd like to talk to you about one of the unique features of RISC-V, and that's the ability to extend the instruction set and add custom instructions, and I'll talk a little bit about how Imperas software can help with that. My name's John Taylor, I'm with Imperas, and we're on the booth just behind here, so if you've got questions afterwards, please come along and talk to us. So before I get into details, let's just talk briefly about why. Let's talk about why custom instructions might be useful for you in your design. And there are a few reasons that it might help. One might be you already know your application. It's something you've been working with for a long time. You know all the details of it, and you know that there are critical loops that you could improve if you could optimize the instruction set. Or even it might not be you need more performance, but you could then get the same performance at a lower frequency and improve your power consumption. It might be you're migrating from a different architecture, moving to RISC-V for the first time, and there are features that are missing in the RISC-V ISA and you want to add that yourself. Or it might be you're trying to combine a couple of elements into a single MCU, taking a DSP and an MCU and building a single solution that brings both of those together. And again, having the ability to customize and extend the ISA lets you do that. So if we talk about, the practicalities, how do you go about developing instructions? How do you go about working out whether it's going to work for you or not? Then, on the right-hand side of the slide here, you can see the sort of typical process you would go through. You take an algorithm, you compile it, you simulate it with a model. You then, analyze the results, work out where your critical loops are, modify the instruction set, add your custom instructions, update your software, and repeat the loop as many times as you need to get the result you want. And using models for this process is much quicker than using RTL design. You can get better profiling information out of the model, and it's much easier to debug the software if it's not behaving as you want. So if we think about the requirements of what a model might need to do, I'm not going to run through all of these. The slides will be available afterwards, so we can work through it. But writing an instruction set simulator is not that difficult at a basic level. It's quite easy to write something that will simulate instructions. But if you're going to get into profiling, if you're going to get into extending that instruction set simulator, actually debugging it and getting it working, making sure it's high quality and it's bug-free, that can take quite a long time. You might want to hook it up to other environments like System C or System Verilog. You want a debugger to connect to it and so on. The Imperas tools, the Imperas models offer all of these features here out of the box and save you time developing that, so you can focus on the core of developing your custom instructions. It's something we've been doing for quite a long time. We've got about 12 years of legacy of developing high-performance, high-quality simulators and models. And so it's a really strong starting point if you want to then continue customizing. We offer models, some of our models free through OVP World. We've got over 10,000 users registered on that website, and that was even before we started looking at RISC-V. So when we think about, when I talk about a model, actually there are kind of two elements to it. One is the description of the CPU, the register file, elements in the pipeline, types of extensions like ALU, floating point, and then you've got the simulator underneath that executes that model. The RISC-V instruction set is very rich, so you have a range of extensions, standard extensions you can include, whether it's sort of bit manipulation, vector, floating point, multiply, and so on. And the spec has evolved over time, and so actually you can see there are several different versions of multiple extensions, and supporting all of those can get really complex and really challenging, but again, it's something we can provide out of the box. And so all of the sort of standard ratified extensions we've already got support for. A lot of what we offer is also user configurable and parameterizable, so you can take that out-of-box model, you can choose which of these features you want to support, which of these features you want to use, even before you get to looking at customizing it. And then, if you want to add your own extensions, whether it's instructions, whether it's CSRs, status registers, there's a very well-defined API and set of libraries to help you do that, and examples shipped with it. And so, we provide that very powerful base. We provide an easy API for extending, and you can add exactly what you need, link it with our tools and profile, and develop your code accordingly. So if we go back to that flow at the beginning, when we think a little bit more about, what are we doing with our C application, our embedded application, often initially you need simulation, you need trace and debug, you need some profiling, and custom instructions are added to optimize a small subset of that. So if we start by profiling the code, that gives us a starting point, gives us an idea of where we'll need to optimize. And so we've got an example here, taking a character stream encoder, doing an encryption algorithm. We've cross-compiled it, targeting sort of fairly simple RV32 IM ISA. We've got our instruction-accurate simulator running it. And we can see here that actually it runs very, very quickly. If you're simulating an embedded core, actually often our simulator is faster than real time. You can achieve billions of instructions per second on a laptop on a standard PC. So that makes it really quick to run even quite complex applications and get your profiling out. With profiling tools, we can now look at that application code. We can look at the time we spend in each function. And we can see here there's a particular function called process line where we're spending about 20% of our time. So that looks like a good candidate to go and look at in more detail and think about what we could optimize there. So we need to think about what instructions might benefit. There are some restrictions on, if you're not used to ISA design, you need to think about what you can encode within the instruction space, how many input registers you want, whether you want immediates, how many control functions within that instruction you need. So, you have to think about the encoding space you've got, but once you've got that, the RISC-V architecture manual gives some guidance about how to extend where your encoding space is. You can follow standard templates of these instructions, so it's relatively straightforward. Add those into the model, and you can, you add an extension library. You don't have to touch the core model. You can add this as a completely separate code base, so you're not affecting the core model. So from a test and development and maintenance point of view, it's very easy to do. Recompile the code, resimulate with a new library, and you can see that the instruction count and simulation time have been reduced quite significantly. If we reprofile the code now, again, we're using instruction-accurate simulation. It's not fully cycle-accurate, so when it comes to doing implementation, you'll probably want to retest this as well. But in the early phases of design, actually, IA is often all you need. You can get a really good feel for whether it's going to work or not. And we can see that process line function has now got significantly quicker. It's gone from 20% of the runtime to 15% of the runtime. And you can carry on in that loop if you want. Go back and look at the same critical paths, maybe try a different combination of instructions, or look at different critical paths now because you've changed where the slowest part is, and go through that loop of characterization, new instructions, resimulate and retest. And finally, when you're done, you can think about optimization, and then you get into thinking about testing it as well. So have you tested all the corner cases for that instruction? For things like arithmetic, have you tested overflow cases? Have you tested negative? And you can develop coverage to check that as well. You might want line coverage for, is your function code all being executed? And you can auto-generate some documentation for that as well. And then before you deploy it, you might then want to run things like compliance tests to make sure you're within the envelope of the specification. You might use the model as your golden reference for your RTL development. So when you come to develop your RTL, you've got something to verify it against. And again, we can provide tooling around that. We have a flow, and I'm giving a conference talk later about how you can do DV using the Imperas reference model. And ultimately, you end up with a complete environment for doing software development. Your software guys can start using that model for their software development early on. And you end up with a very scalable system. You can also develop a virtual platform. So when you're before your silicon's ready to go to customers, you can provide a virtual platform environment for them so they can start their software development. So when the silicon arrives, they've already got software ready to deploy. And all of our tooling works, it's designed around these extension libraries. It's designed to work around these custom instructions. So we can see here we've got some disassembly, we've got some extra state registers visible in the debugger, and the trace disassembly shows as well. It's not just showing hex code that you've got to work out yourself. So with that, I want to say thank you very much. That's a very brief, very quick introduction to custom instructions and why they might benefit you. But thank you for your time. If anyone's got questions, I'm happy to take them now or have a chat afterwards.